uh, in thermal expansion, what is coefficient of thermal expansion, coefficient of linear expansion? Coefficient of linear expansion of solid, alpha. You know, it is L2 minus L1 by L1 into T2 minus T1. And this is delta L by L delta T, even we can write. Right? Well, then what is the change in length? Change in length delta L. L alpha delta T. We can write this. Already we discussed all these topics in detail in the previous chapters. Okay. And somebody asked me a question, sir, this alpha value, is it same for isotropic and anisotropic material? I think this is also discussed in the last class. For isotropic material, alpha value is same in every direction. So average alpha is simply alpha only. When we come to anisotropic material, when we come to anisotropic material, that name itself tells you it is an anisotropic material. Its expansion is not same along the three axes. It differs. Along the x-axis, expansion is different. Along the y-axis, expansion may be different. Along the z-axis, expansion may be different. So those expansions are different along different axes. That you call it as anisotropic material, right? The first thing you need to know is thermally anisotropic. The expansion is different along different axes. Whenever expansion is different, their alpha values are different. Along x-axis, alpha value is alpha x. Along the y-axis, alpha value is alpha y. Along the z-axis, let us take alpha z. Then, what is the average coefficient of linear expansion for this material? Average of alpha x plus alpha y plus alpha z by 3. Right? Use this formula, alpha x plus alpha y plus alpha z by 3. You get alpha of that particular material, anisotropic material. In the problem, they may give these values, alpha x value, alpha y value, and alpha z value. I hope that in yesterday's paper you got this problem. In yesterday's paper, you have that problem, it seems. See, alpha x plus alpha y plus alpha z by 3. So, for isotropic, what, sir? For isotropic material, see, the best example of isotropic materials are metals. General metals, whatever we are discussing, they are isotropic. For isotropic, alpha x is equal to alpha y is equal to alpha z. All are same. Alpha x, alpha y, alpha z. All are same. Whenever they are same, average alpha, all as they are same, just I am taking them as alpha, then alpha x plus alpha y plus alpha z by 3. Is it not equal to alpha? Simply as they are same, as these are same, it comes as 3 alpha x by 3. 3 get cancelled, you get alpha x. In 3 directions, alpha value is same. In general material, whatever we take, isotropic. Some of the crystals, they exhibit this type of property. In the problem, they clearly mention whether it is isotropic or anisotropic. How to identify in the problem, sir? If they give different values of alpha in different directions, treat it as anisotropic. If not, it is isotropic. Clear? Well. Come on, if you want to write down. I hope it is completed in the last class. And I hope we discussed how the time period of a pendulum changes with temperature. Already we discussed in the last class. Variation of time period with temperature. What is the relation between alpha, beta, gamma? What is the relation between alpha, beta, gamma? Already you know it. Just for the exam sake, I am revising. Relation between alpha, beta, gamma. For a solid, where alpha is coefficient of linear expansion, beta is coefficient of areal expansion, gamma is coefficient of volume expansion. What is the relation between those three? You know, beta is equal to 2 alpha. Beta is equal to 2 alpha. And gamma is equal to 3 alpha. You know it very well. And what is the relation between beta and gamma? Gamma is equal to beta by 2. Sorry, 3 beta by 2. Am I correct? Or from these two you can derive gamma is equal to 3 alpha, alpha is equal to beta by 2, alpha is equal to beta by 2. In place of alpha, simply from this alpha is equal to beta by 2 you take it and you substitute it here. So 1.5 beta gamma is clear. When it comes to anisotropic, first find alpha average, apply the same principle. Apply the same principle. How the time period of oscillation of a pendulum varies. Time period of oscillation of a pendulum varies with temperature. Oscillation of a pendulum with temperature. Already we discussed it. See, whenever temperature increases, length of the pendulum increases, then time period increases. Whenever time period increases, clock runs. Clock runs slow. Just refer your notes. When temperature increases, length increases, time period increases, the clock runs slow. Whenever clock runs slow, what happens? Clock loses time. It loses time. Whenever temperature decreases, length decreases, time period decreases, then clock runs fast. Yes or no? Clock runs fast. Clock gains time. See, we are simply telling it is losing time and gaining time. How much loss or how much gain of time? How much loss or how much gain of time per day we calculate it, right? What is the formula? Loss or gain of time per day, because this is the important formula we use. What is the loss or gain of a time per day? How much it is? Delta T. Half. 86,000. Am I correct? See that 86,400. Yes, 86,400 alpha delta T. Loss or gain of time per day. Half of 86,400 alpha delta T seconds. Right? This formula you need to remember. Based on this, even we solved some problems also. Okay? And we discussed even bimetallic strip in the last class. Bimetallic strip is a combination of two metals. Combination of two metals which are riveted together. Whenever there is a change of temperature, they bend. Bimetallic strip, it is just combination of two different metals, metal strips, thin metal strips, combination of two thin metal strips, right? This is one strip and this is another strip. If each of thickness T, their distance is taken, this total thickness is taken as D, and each of thickness T, right? Then the D becomes 2D. Is it same? Well, notations also same. Well, and it is made of material alpha 1. This is made of material alpha 2. So two metals of different material. Whenever the different word comes, their alpha values are different. Whenever it is heated up, what happens? When temperature rised, it bent like this. It bent like this. Alpha, whose in these two, the question comes in the exam is which metal comes on convex side, which metal comes on concave side. Whenever it is bent like an arc, which metal comes on convex side, which metal comes on concave side. The thing is, the metal whose alpha value is greater, it expands more for the rise of temperature. So it comes on convex side. Already I gave the reason also. So here alpha 1 is greater. When temperature rise, it comes on convex side. Whose alpha value is lesser, it comes on concave side. So it takes a curved shape, right? Then what is the, when it takes a curved shape, what is the radius of curvature? What is the radius of curvature? This radius of curvature. See the average, the thickness of the bimetallic strip is D. Then what is the formula? R is equal to D by alpha 1 minus alpha 2 into delta D. Right? This is the formula. What is D there? Thickness of the total bimetallic strip. Thickness of the total bimetallic strip. Total thickness D. If they ask the same in terms of thickness of each strip, then thickness of each strip, what happens to this? Is it correct now? D, T by 2. I hope correct. See, when temperature falls, then what happens? When temperature falls, it takes this shape, which comes on concave side, which comes on convex side. The metal whose alpha value is greater contracts more. Always the key point here is the metal whose alpha value is more. It expands more for the rise of temperature. It contracts more for the fall of temperature. So here on convex side, you get the metal of higher alpha value. On concave side, on convex side, the metal of lower alpha value will come. Okay. As it is taking a curved shape, here also there is a radius of curvature. Same formula. So this is what we discussed in the previous classes in detail. Today we are going to discuss a very important application, measuring tape. It is not discussed in the last class. Measuring tape. Come on. How the reading given by a measuring tape varies with change of temperature. How the reading given by a measuring tape varies with change of temperature. First, when it varies, whenever that measuring tape is made of a metal, a pure metal like copper, iron, silver, gold, if it is made of metal, that measuring tape, we know whenever temperature changes, its length also changes. So the reading shown by that measuring tape varies. Okay, how it varies? Let us see. The important point is that the tape is made of metal. And the tape is made of metal. Then it shows wrong reading. Then it's reading with change of temperature. With change of temperature, the reading shown by the tape varies. Right? For the Any measuring instrument gives the correct reading at its calibrated temperature. Measuring instrument gives the correct reading at its calibrated temperature. Right? Note point is any measuring instrument gives correct reading at the temperature where it is prepared. Where it is prepared. The temperature you call it as calibrated temperature. Calibrated temperature. Right? The temperature where it is prepared, I am taking it as TC. Calibrated temperature. So it gives correct time at TC. Right? Well. Take a measuring tape. This is a measuring tape. These readings are engraved on the tape. Calibration means assigning the readings on the tape at some particular temperature called calibrated temperature. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like so. This is a tape. 1, 2, 3, 4, like this, the values. By using this is prepared at the temperature TC, calibrated temperature.